Parallel equivalents. There are also four characteristics to parallel resistors, just like, to parallel equivalences, just like it is for series. It's resistance, voltages, current, and sources. How do they behave when they're in parallel? So let's talk about parallel resistance. We know that parallel resistances add inversely, but the question is why? It's the resistance equation. The resistance equation shows that the resistance is equal to 1 over the it's the resistivity, the length divided by the area. So when I look at just the geometry piece, it's 1 over the area. So that means here that the resistance in parallel configurations is 1 over the area. Adding resistors in parallel is equivalent to increasing the effective area, as we've said. So adding resistors in parallel effectively increases the effective area. Seen by the incoming charges. So we can group parallel resistors into an equivalent. So if I have resistor something like this, where this is resistor 1, 2, and this is resistor N, I can reduce all of these resistors into one single equivalent resistor, which we call R parallel. But since I'm adding them in resistance, we then say that a group of parallel resistors can be replaced by a single equivalent resistance. Where 1 over R parallel, and this follows directly from the resistance equation, is the sum of the inverses or the conductances like this. You know, I said conductance, that is not correct. So if I come in here, this is what we mean right here. So any branch in a circuit can be replaced with that. So circuit-wise, this is what we want to do. What we're going to have here, excuse me, is I'm going to have some circuit. And what we're going to do here is that we are going to isolate one of the branches. So if I have one branch that's in parallel like this, then this is what we will do, right? So if this is 1, 2, 3, we will then make a parallel equivalent. Where now I just replace this circuit with one element. It's effectively the same thing. So then I could then replace this guy with R parallel. So now let's go to voltages. 2. Parallel voltages. All parallel elements have the same voltages. Since there are only 2 nodes. So picture-wise, I could come back in here and I could stick in my circuit right here. And so when I look at this thing, what you're seeing here is that the top node is this guy. And then I can choose a ground down here, or I could choose any other node voltage. Only the difference matters. And then down here, we'll just say that this is our relative ground. And then this guy up here becomes our V branch, where again, this is the voltage across the branch. So that means here is that because there's 2 nodes, that tells us then that if I look at each of these individual resistors, and I could call this 1, 2, and 3, we could then say that V branch has to equal the sums of V1, V2, V3. Now, moving on to parallel currents here, there are 2 ways to divide currents. We've talked about KCL already. So when I think about KCL, that just tells us that the current of the branch has to equal the sum of all of the currents. One that's less familiar is the current divider rule. The current divider rule says that it's the current of the nth resistor is going to be equal to R parallel divided into Rn, times the branch current. So I would say that in general, CDR is or should be used when doing resistor reduction techniques. It's the easiest. So what we want to do here is that we want to derive CDR. It's fairly straightforward. So to derive CDR, focus on the equivalent circuit. So if I get a picture of this, and I think we have this over here, so let me grab this. So if I copy this and bring it down here, I can then place this guy right here. So what am I seeing here? What I'm seeing here is that I have these branches, node voltages that we've talked about. And then we have our ground. And then we already know that this guy is V branch. Note, V branch is on the left, but I'm not going to put it there. So what we want to focus on is we want to focus on what the branch current does. And what it does here is it goes down this circuit and it divides the currents. And then here we have I branch coming in right here in the equivalent circuit. Since voltages are the same, in other words, V branch has to be the same as V1, V2, all the way to some Vn, and using Ohm's law, here's what we have. Since V is equal to a constant, I can replace each of these voltages with Ohm's law. So in other words, I can replace I1 times R1. I can replace R2 plus I2. And I can just keep going on, and I could have Rn, In, and that has to also equal R parallel times I branch. So what we want to do here is that we want to focus on this guy right here. So if I do the algebra, or rearranging the terms, we find that I can write a relationship of In is going to be R parallel divided by Rn times I of the branch. And this is what we call the current divider rule. CDR. And you could see that all of that really is about KCL, or just, knowing how KCL and KVL behave in parallel circuits. So again, Kirchhoff's laws are the basis of the circuit analysis. So physically, what does this mean? Well, there's two things to think about. One, the current through a resistor is inversely proportional to its resistance. In other words, the current IN is proportional to 1 over the resistance. So in other words, if we have a large resistance N, then that means I'm going to have a lower current, which then tells us here that I of N is then going to be proportional to a large resistance here. On the other hand, if we have a small resistance, then we're going to have a higher current. So in other words, we have a higher current because the resistance is smaller, which we knew that already, but at least you're seeing that intuition and built into the current divider rule. And another thing here is that when you look at the details of the CDR, you could see that there's this term. So in CDR, we see that we have this term R parallel divided into Rn, and this turns out to be the percentage of current through a parallel resistor. So that ratio is telling us exactly what has to happen. So then our last thing that we got to focus on is on sources. So our fourth characteristic is that we want to talk about parallel sources. And we need to talk about voltages, and we need to talk about parallel current sources. So let's talk about voltage sources. Parallel voltage sources must all have the same voltage values. So if I look at a circuit here, let me see if I still have this, and let me see if I could just modify this. Okay, good. So what I'm going to do here is that I'm going to erase this, and I'm going to erase the resistors here. So what I'm seeing here is that I have a voltage source here. And then what we'll do here is that we'll change the polarization of these voltages. Oh, I can't do that. So let's say that we call this guy V1. We call this guy V2, and we're going to call this one right here Vn. So the first thing that we see here is that there's only two nodes in the circuit. So we see that this guy has to be V branch, and the other one has to be the ground. So in this situation, we're seeing that V branch, because there's only two nodes, it must have these polarities. All of these guys must be the same here, regardless of what their orientation is. That must be the case. Now, what if that's not the case? In other words, if parallel voltage sources do not have the same voltages, the voltage sources will discharge. And when we say discharge, that means it is damaged. It's damaged during the discharge, so it will discharge to the power supply, power supply with the lowest voltage. So they continue to discharge until they get to the lowest, until all of them have the same voltage. That actually damages it. So if you had a 10-volt battery and a 12-volt battery that were in parallel, the 12-volt battery will discharge till it reaches 10 volts. So they must be in parallel. I mean, they must have the same value when they're in parallel. So now let's talk about current sources. So we want to do the same thing that we did before here. And I'm going to borrow this image because I could convert them into current sources quickly. And so what we want to do here is that I want to, so suppose we have parallel current sources. So I'm going to modify this thing. So now what I'm doing here is that when I'm looking at that, I'm not interested in voltage sources anymore. What I'm interested is current sources. So now let's say that I have a current source that this one goes up, This one goes down, and if I follow the same, maybe this one goes up too. And so I'll say that this guy is source 1, this one is source 2, and this is the nth source. So when you look at this thing, now remember there's a connection here with these branches here. We can see here is that I'm going to have a branch current that's coming in. So now if I apply KCL, here's what I see. I see that the branch current, that's the current coming in, has to be the sum of the currents going out. So if I look at the currents coming in, you could see that I1 and IN are coming in. So then I'm going to say plus I1 plus IN. And then again, we have a series of these. And then I can see that the only current going out is I2. So I'm going to go minus I2, and that has to equal to 0. So if I now solve for I branch, this acts as an equivalent, tells us the equivalent parallel current source value. In other words, I branch can also be written as minus I1 plus I2 all the way to minus IN. So I can replace all of these with one source. You know what? I'm going to modify this picture again. So that means here is that if I take just 2 of these and I copy them, and let's say that I paste this right over here, that means I can replace this guy, this circuit, with a current source that reads I branch. Now, you know what? I'm running out of space. So I'm going to manipulate this just a little bit. So I'm going to put this right here. I'm going to move this down. So if I look at this thing, this is going to be I branch. And I can replace it with this parallel equivalent right there. That's what I mean by that. So that's how, so that means I can replace it. So now what I want to do here is that I want to do a couple of things. Now that we've done over the 4 characteristics, what I want to do here is that I want to look at some examples. I want to start with an example, then I want to show you 2 tricks that I'll give you examples. So as an example, let's say that I have this circuit here. So in this case, I want to determine all the resistor currents. And of course, using CDR. That's what we want to do. Now, the fact that there are 2 nodes connecting all these elements, we can move elements for convenience. Okay. Remember, since parallel circuits have the same 2 nodes, one can move elements for convenience, which then make the calculations considerably easier. So let's try to do this now. So let's say that I have this circuit here. Okay, so and I have a parallel branch. So I'm going to go, so I'm going to say one resistor here. And then I'll put in the values a little bit later. And I'll have one resistor here. Then I'm going to have a current source. Nope. Then let's say that I have a resistor. And you could see that I'm purposely mixing these guys up. And then let's say that I have another current source here. So I can arbitrarily pick the directions of these currents. And then I'll arbitrarily give them values. So let's say that this is 9 amps. This is 6 amps. And this is 3 amps. And then I have resistor, let's say that this is a 12 ohm. This is a 6 ohm. And then this resistor here is going to be a 3 ohm. So what I mean about moving these resistors, I can use parallel reductions. So if I use parallel reductions, I mean, just remember, there's only 2 nodes here, right? This is what allows me to move them because they always see the same values. So now, because they have the same values, what I'm going to do here is that I'm going to combine all of the current sources together. So look what happens. I can take all of these current sources and I could branch them all together. So in other words, I could take one current source. Now note that both of them, I have 9 and 6 going up, but note that 3 is down. So what I'm going to do here is I'm going to say I have a current source. And now I'm going to add them together. And I'm going to say that the current here is actually going up. So then if I look at the current sources, note that that's 9 amps plus 6 amps minus 3 amps. And then if I look at the resistor, I have 3 resistors in parallel. So I could now come in and I could go, I have this resistor, and I have a circuit like this. So then I could see that this is my 12, this is my 6, and this is my 3. So we're not done with the equivalent part, but let's focus on that. Let's keep reducing it. So now reduce the resistances. So the way I reduce them is that I know that 1 over R parallel in this case is then going to equal to 1 over 12 plus 1 over 6 plus 1 over 3. And when I compute that number, I'm going to get that R parallel is equal then to 1.5 ohms. So now you could see here is that I'm going to have, if I add these guys together, you could see that I have 15 minus 3. So this has to be 12 amps. So now here we have our reduced circuit. So the reduced circuit is then going to look something like this. I have my branch, and I'm going to have what? I'm going to have one current source, and that current source is going up, and this guy is going to be 12 amps. And note, I have that parallel resistance, but what I'm going to do here is that I don't want to reduce it to just a parallel resistance, because I want to use CDR to calculate the current. But here's our 12 ohm. Six, and then finally 3. So what we're seeing here is that what's happening to the currents? In this branch, what we're seeing here is that these currents are being, I'm guessing here that if this source is active, then I'm going to have a polarity that goes minus plus. Okay? So now if I focus on this thing and I can remove this thing from the circuit, I'm going to apply CDR on these resistors. So in other words, if this is an active circuit here, what does this tells me here? If this is an active circuit, I'm going to have, let's say, a current coming down this direction right here, which I'll call I12. Oops, I didn't write that very well, did I? I'm going to call this I12. And why am I doing that? Because this node here is the positive node. So that means the currents must be going down. This node here is going to be the negative node. So now, using CDR, I'm going to pretend that I could calculate this. So then I'm going to come in and I'm going to say, okay, so this is the current across the 6, going like this. This is the current across the 3, going down. So now if I use CDR, it goes something like this. Applying CDR, I'm then going to get what? I'm going to say that the current across the 12 is going to be the parallel resistance divided by the resistance of the 12 ohm resistor. So if I times the branch current, and in this case, we'll say that the branch current is that 12 amps. So when I look at this thing, then I could then write that this is 1.5 divided by 12 times 12, and that gives me a value of 1.5 amps for I12. And then if I go the current being 6 here, again, that's going to be I branch divided by the resistance, but now we know that this is 1.5. Now we have the resistance 6 times 12, and so if I compute that, that gives me 3.0 amps, and this guy's going to be I6. So when I'm looking at this, what you're seeing here is that look at the higher resistor has the lowest current, but you could see that the resistance 6 is half of that, so it doubles the current here. And then finally, if I look at the current 3 ohms, this will then be 1.5 divided by 3 times 12, and this would then give me 6 amps for I3. So that's how I would use the current divider rule. Now note, this is not really properly done. And the reason why this is that note that there is a current that's coming in here. But This is how you would apply if you had an isolated 12 amp source with these three resistors. Now let's go to these tricks that I want to talk about.